This is step 6 in my final project, and just for reference, I'm working with a data set that contains NBA player statistics from the years 2018 to 2021. The first question I asked was, can every stat for a player in the dataset be used to predict if they're an efficient defender? Specifically, can we predict if a player is a good blocker, and what characteristics can we determine based on these predictions? In addition, how can general managers use this information when evaluating their team's needs and looking at players of interest? We asked this question to get a better understanding of what variables can be used to predict if a player is good defensively. Though the NBA tends to favor superstars and high-scoring players, if you look at the trends of which teams have won the championship in the past couple years, every team has a very strong defensive presence and key players that contribute to that success. For the question here, we used every continuous variable in the dataset to predict if the player was an above-average blocker. Blocks are one of the most important defensive statistics, and when looking at that number, general managers can usually determine how efficient a player is on defense and how much they contribute to the team's success. The first step I took in solving this problem was looking at the average statistics of every player in this dataset. This way, I was able to get a threshold value to determine if a player was above average or below average in some defensive stats. Looking at these averages, it's interesting to see that all the defensive statistics are much lower than the offensive ones, which makes sense because coming into the league, you want to prove that you can provide some sort of value offensively to the team. Otherwise, most teams are very unlikely to draft you. For this question, we wanted to look at these lesser looked at stats and determine what it means when looking at a player's overall defensive efficiency. After acquiring the mean blocks of every player in the NBA through the 3 seasons, I created a new column in the dataset called Good Blocks, which returned 1 if the player had above the average blocks, which is 0.38, and 0 if they are below average. Next, I cleaned the dataset by removing variables I thought would not contribute to the model's overall accuracy, like name, position, and team, and I took out blocks, which is the value that I was trying to predict. After setting up the linear regression model, I used every single variable in my clean dataset as my X predictors and used the new column Good Blocks as my predicted Y value. For model validation, I ran a train test split where 80% was dedicated to the train and 20% was dedicated to the test. After z-scoring the variables, I fit the train and test set and created a Y predicted value, which was the model's prediction if a player was a good blocker or not, and then printed the model results. When looking at these model results, the R squared explains how much of the R squared shows how much of the variance in the data set the model explains. Typically from 0 to 1, 1 means that the model explains all the variation in the data set, which is what we ideally want. 0 meaning it explains none of the variation in the data set. For my train set, I had 1 for my R squared value, which was very good, and a very low mean squared error value. The mean squared error is basically a loss function that shows us how well the model performed, and though there isn't an ideal mean squared error number, the lower it is, generally the better the model performed. But when I look at the test performance metrics, the R squared varied a little bit, meaning it explained a little less of the variation in the data set, but there is a huge jump from the train mean square error to the test mean square error. This is something I was not looking for, and it shows clear signs of overfitting in the model. Overfitting in the model is when the model is trained very specifically on the trained predictors and performs very poorly when exposed to unseen test data. Since the model was overfit, it was not looking good for this question, but it set me up well for my next question when I saw what were a couple ways I can try and fix this. After getting the results from my model, I try to visualize the findings through a ggplot. Using the clean dataset, I plotted steals against defensive rebounds and colored the data points by good blocks, which is the categorical variable I was trying to predict. In the ggplot, I used the two other most important defensive statistics, steals and rebounds, and saw what it meant when a player was an above average blocker and below average blocker, and if I could determine what type of player that would be. When looking at the cluster that shows us players who are below average, the ggplot shows us they have generally low defensive rebounds, but a lot of players had above average steals. On the other hand, when looking at players who are considered good blockers, they typically had above average rebounds and a lot of steals. I use this information to determine a few things. Firstly, the starting lineups of NBA have a pretty big deviation of height from the shortest player to the tallest player. Typically, the smaller positions like point guards and shooting guards will have lower defensive rebounds just based on their height, but have a lot more steals because they are more active, agile, and usually the center of attack for most offenses. The cluster characterized by below average blocks can be characterized as smaller position players who get lesser defensive rebounds but above average steals. The cluster who can be characterized as above average blockers can be seen as players who are much more efficient defenders, getting more rebounds and steals. I specifically characterize these players as small forwards and power forwards, which are some of the bigger positions, as they have the height advantage over smaller players getting the rebounds, but are more agile than centers, which is why they're more efficient with steals and produce a higher number of them. Using this ggplot, general managers can determine if they are looking for players to boost their defensive efficiency, and if they should target small forwards and power forwards, as they can kind of tell that they will always have an above average amount of blocks while providing other good defensive statistics. The next question I asked, based off the last one, was when performing principal components analysis, how can we reduce the predictors in our model to only include the most important components when predicting if a player is a good blocker? Next, how many components are required if we want to retain 90% of the original dataset's variance? And does this dimensionality reduction help or hurt our model? Since my last model was overfit, I determined one of the reasons for this was that there are too many predictors in the model that I built, which makes sense since I use every single player statistics, excluding a couple. Principal components analysis asks us, is there a better set of axes that I can use to more efficiently describe this data? These principal components can better describe the variance while using significantly less predictors by combining the variables into these components. Since my last model was overfit, I thought performing dimensionality reduction through principal components analysis could drastically improve the accuracy of my model. I started by setting the initial n components to 10, which is a big reduction from 25, and then got the explained variance ratio, which shows how much of the variance of the original dataset these 10 components explain, which was around 95, which is a good number that I looked for. I then ran linear regression using a new X-train with the PCA and acquired the model evaluation results. As I hoped, the test scores provided a much better R-squared and mean squared error than the first model. Not necessarily a lower mean squared error or a higher R-squared, but it showed not as heavy signs of overfitting, which is what I was hoping to fix with principal components analysis. With a more similar R-squared and mean squared error, it showed that the principal components analysis fixed this problem of overfitting through the dimensionality reduction. Next, I created a data frame showing the explained variance of each component and the index of what it was. Based off this data frame, I saw that the first three components explained about 75% of the variation in the original dataset, which is a big step up from using all 25 variables to explain all the variation. Finally, to answer the original question of how many principal components are required to explain 90% of the variation, I determined that about 7 principal components would be sufficient. In the end, I was able to create a model that was not overfit and perform well when asking to predict if a player was an above average blocker and how we could use that information to determine what type of player he is.